Okay, let's just skip the fluff, all right? We are going to focus entirely on one goal today: achieving maximum marks with minimum effort in your Cambridge IGCSE computer science exams. To do that, you really need to understand the programming workflow, how to abstract algorithms, and exactly how the examiner is evaluating your answers. Consider today's explainer your ultimate shortcut. We are literally going to rewire how you look at exam questions and hand you the exact tools you need to secure those top band grades. So, let's get started.
Take a look at this answer real quick. An echo check is when the computer sends data and checks if it matches. Now, if you're sitting in an exam right now, under pressure, this probably looks like a perfectly reasonable, logical response, right? I mean, it sounds correct, it makes intuitive sense, but here is the painful reality for thousands of students every single year. This answer is an absolute trap.
That generic answer earns exactly 0 marks. Nothing. Nada. Zilch. And look, in a highly competitive subject like computer science, dropping easy marks on core concepts like data transmission could literally cost you an entire grade boundary. The examiner isn't looking for a casual chat here. They are looking for precise, technical vocabulary applied to a very specific framework. But before we can go ahead and fix this answer, we actually need to fix how you process information.
All right, moving into our first section, Abstraction and Decomposition Masterclass. To stop losing marks, you've got to stop thinking like a student reading a textbook and start thinking like a programmer designing a system. And that begins with these two foundational tools. First up is abstraction. This is simply the act of removing unnecessary details to focus only on the relevant information needed to solve a problem. Think of it as basically clearing out the mental clutter. You know, when a real computer scientist looks at a complex system, they don't look at every single moving part. They strip away all the noise until literally only the core logic remains. And this brilliantly illustrates how abstraction works in the real world, straight from the Cambridge syllabus. Imagine your problem is programming a robot to make a cup of tea. Okay, so you have tea bags, milk, sugar, a white mug, water, a kettle. Well, through abstraction, we immediately ignore the color of the mug. Why? Because a white mug or a blue mug absolutely does not change the logic of making tea. It's irrelevant data. We drop it. And this is exactly what you must do when you're reading those massive paragraph-long exam questions. You have to filter out the noise and find the programmable data.
So the crucial point here is, once you've abstracted the problem, you must break it down. This is called decomposition. You can't just yell at a computer, "Make tea." You have to split that massive, complex problem into much smaller, manageable chunks. Step 1. Water. Fill the kettle and boil it. Step 2. Combine. Add water to the tea bag. Step 3. Personalize. Add the milk and sugar. And finally, step 4. Serve. By decomposing the problem, what was once this overwhelming task is now just a straightforward series of simple, solvable mini-problems.
Next up, section Designing Your Algorithm Workflow. So once we actually have our decomposed chunks, we need to arrange them into a formal workflow. This is a set of sequential instructions that a computer can actually execute. When you're designing an algorithm from scratch, a programmer must always define 5 mandatory stages. First, inputs. What raw data is actually going into the system? Second, outputs. What should the final result look like? Third, order. What is the strict, logical sequence of events? Fourth, decisions. Are there any conditions like, if the tea is too hot, wait? And fifth, repetition. Does a step need to loop, like stir 3 times? If you map out these 5 steps, you can honestly write any algorithm the exam throws at you.
Now, I want you to keep this algorithmic thinking fresh in your mind, because in just a moment, I'm going to show you the hidden examiner clue that changes your exam answers completely. It's a clue that guarantees top band marks. But first, to really make that framework obvious, we need to apply this workflow logic to a high-stakes scenario.
Which brings us to our next section, Securing Data with Error Checks. This is honestly one of the most critical topics in Paper 1. When millions of bytes are just flying across the internet, data gets corrupted, and we absolutely need algorithms to catch those errors. Okay, here is where precision really matters. Notice the stark contrast between these two methods. A checksum uses an agreed-upon mathematical algorithm. The sender calculates a value from the data, sends it, and the receiver performs the exact same math to see if the values match. There is a strict protocol here. But an echo check, well, an echo check has no agreed protocol before transmission. The receiving device simply sends an exact copy of the data straight back to the sender, and the sender compares it to the original. It's a completely different mechanism, and the mark scheme demands that you know this exact difference. All right, section, the high mark answer framework. We are finally ready for this. You now understand algorithmic logic and technical precision, so it's time to combine them into an unstoppable exam strategy.
Consider this simplified trace table for a linear search algorithm. Say we are looking for the game Tetris. A linear search looks at every single item in a dataset sequentially, just one by one until a match is found. So it checks index 1, chess, no match. It moves on, checks index 2, Tetris, yes, match found, search complete.
So here is your challenge. If the exam asks you to describe the linear search process shown in the table, how would you actually write it to guarantee full marks? Don't just give me a generic answer here. I actually want you to pause this explainer right now. Apply the technical precision we've been talking about and predict the perfect answer in your head. Go ahead, take a second.
Okay, let's see how you did. To ensure literally no marks are ever left on the table, you must use this ultimate four-step framework for any scenario question. First, state the concept clearly. Second, provide evidence or data directly from the scenario. You have to use the nouns they give you. Third, provide the scientific reasoning, like how does the mechanism actually work? And fourth, wrap the whole thing in precise examiner wording. If your answer was just something like, it searches until it finds Tetris, well, you missed the data, the reasoning, and the technical vocabulary.
Let's move to our final section, upgrading your final answer. To bring this entire explainer full circle, we're going to apply this exact four-step methodology to that flawed exam answer we saw at the very beginning.
Look at this incredible transformation. The flawed answer was, sends data and checks. It's weak, it's generic, and it earns exactly 0 marks. Now read the upgraded answer. The receiving device immediately sends a copy back to the sender for comparison to detect differences. Look at the precision there. We specify the receiving device, we state the mechanism, sends a copy back to the sender, and we give the reasoning for comparison to detect differences. This upgraded answer is totally bulletproof. It uses Cambridge-safe wording, it demonstrates a real understanding of the algorithmic mechanism, and it easily secures the full marks.
By mastering abstraction, algorithmic workflow, and this highly structured answer framework, you've honestly just given yourself a massive advantage. But ask yourself this: if you can debug an exam question this easily, what happens when you start debugging the actual code? Because knowing the theory is really only half the battle. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Seriously, jump straight into our next explainer on trace tables right now, because taking this theory and tracking the variables line by line is the ultimate key to completely conquering Paper 2. I will see you over there.